Now we will try to understand what does autocorrelation and power expected density tells about the random process. So we will start with one example. Let's take a random process xt, and suppose it takes at any time it takes only two values, +1 or -1, and both values are taken with half probability. Now let us focus on two time instants xa and xb. Suppose random variable is such that these two values are the same always. In that case, what if I compute the autocorrelation? See, when I say they will the same means if xa is 1, xp will also be 1, and if xa is -1, xp will also be -1. So if I compute the autocorrelation here, which is nothing but the expectation of product of xa and xb, we can notice that xa into xb, either both can be 1, so product will be 1, or both can be -1. In that case, the product will also be 1. So it either takes +1 value with half probability or also takes +1 value with half probability. So in that case, the expectation is just 1. Let us take another example. Suppose random process is such that these two values are always the opposite. So whenever xa is +1, xb is -1, and whenever xa is -1, xb is +1. In that case, if you compute this product, whenever xa is +1 with half probability, xb is also a -1, so product is -1. And whenever xa is -1, xb is 1, so product is also -1. So both occurs with half probability, so expectation of this product is also -1. So these two cases represent two scenarios where you can tell what is the value of xb from the values of xa. From first case, because they are equal, if I know xa is 1, I will tell xb is also 1. In the second case, they are always opposite. So if xa is -1, I will tell xb is 1. So that's why I'm getting this very high values of correlation, autocorrelation, which kind of tells that there is some dependence between the two. Let us see one more example. Suppose RP is such that these values are independent. In that case, xa and xb both can take +1 and -1 independent of each other. So then there will be total 4 cases possible, right? One would be 1, 1. Another would be where 1 is -1, another is 1, or 1 -1 and -1 and -1. So what will be the product in those cases? So product will be 1 with half 1 by 4 probability, -1 with half 1 by 4 probability, -1 again with half 1 by 4 probability, or -1 with +1 with 1 by 4 probability. If you compute the average, you will get 0. So it kind of tells that when these are independent, you may get autocorrelation to be a very small number like 0. So again, so autocorrelation kind of tells something about the independence or dependence, but of course it is not, it doesn't exactly imply independence, because autocorrelation only talks about the second moment, like it's the product of xt1 into xt2, while the independence is actually when you talk about the independence of the distribution of at t1 and t2. So it involves all the moments, not just the second moments. But there is some information which can be guessed from the autocorrelation. So let us see this example. Suppose Rxt is delta t. So how does this look like? It means at whenever t is 0, the delay is 0 between the two time instant, then you get a very high value of the correlation, and rest places it is 0. So when delay is 1, it means you are looking both xt1 and x2 are same. In that case, there is enough correlation. And then as soon as you just change the time little bit, you go from t to t plus delta t, the autocorrelation becomes 0. It means the signal may become totally independent. Okay. Again, I'm saying may because there are maybe cases where correlation 0 does not imply that they are also independent. So, but there is some case that the signal becomes immediately uncorrelated or independent. Both can happen. And this may be a very fast varying channel which just tells that all you can guess the value of xb from xa only if a equal to b. Right? If they are equal, they're different, you have no information about xb from x. Similarly, let's take the another example when rxt is 1. So what do we get from that? So RXT1 means the correlation is always 1, right? This may show an example where the signal is constant. This means you are able to guess the value, uh, you are able to guess the value always from the value of the value of random process at one time instant. Okay, so here I'm saying it's a high correlation. This is scaled with the amplitude of the random process. Okay, if of course the amplitude is high, instead of plus one minus one, it takes plus two minus two, then it may become as big as 2 also. So from this, let us come back to the power spectral density. So remember, power spectral density is defined for the wide sense stationary process. For a wide sense stationary process, the PSD is defined as the Fourier transform of the autocorrelation function. So if RXT is the autocorrelation, I take the Fourier transform to get the PSD SXF. And because the Fourier prepare, I can also compute the correlation, autocorrelation from the PSD by taking an inverse Fourier transform. So if I take SXF and multiply by e to power j 2 pi ft, and I integrate with respect to frequency, I will get the autocorrelation function. Now, because RXT is symmetric, you can guess RXF should be a real function. And it's also non-negative, which we'll see later on. One thing you can notice that if I put t equal to 0 here, I would get Rx0. And here, if I put t equal to 0, this will become 1. So I will get integration of SXF into df. Okay. And notice also Rx0. So what is Rx tau? It is expectation of xt into xt plus tau. And if I put tau equal to 0, I will get Rx0 equal to expectation of xt into xt, which is xt square. Okay, and if xt is a signal, you can look at xt square as the power of the signal. So this is the expected power of the signal. Okay, so what relation we get is if I integrate this power spectral density function with respect to frequency, I will get the complete power. Okay, so if you recall this as a mass density relation, if you know the density at each point and if you integrate the density over length, you will get the mass. Similarly here, if you integrate this function, you will get the complete power. So that is why this function is known as the power spectral density. It is the density of power over the frequency, over the spectrum. So SSF kind of shows the density of power uh, at frequency f. And if I take a small interval delta f, then SXF into delta f will show the power of the signal in that small interval of frequency spectrum. We will discuss this more later on. So what will be the PSD of these two particular signals which we discussed? RXT is delta t, so the power spectral density would be just 1. Okay, so 1 means it's constant. So what does it tell you? If you get a PSD, constant PSD, it means that the signal has power, equal power corresponding to all frequencies. Okay, and similar thing you can guess from this RXT also. Delta T means the function is changing very fast. Okay, so you cannot predict what will happen next instant. So kind of there is all kind of frequencies. It's like a noise, completely like a noise where the signal can change very fast. Okay, it may have high frequency also, low frequency also, everything. And second example, if we look at Rxt equal to 1, okay, what is the spectrum density in that case? In that case, uh, PSD is delta. So it means there is a DC component of frequency here, right? So there may other signal exist, but overall the signal is not changing on the average, and you are getting a DC component. Okay, and the same interpretation we also got when we try to interpret this autocorrelation. Rxt equal to 1 means the signal is highly correlated everywhere. So from one value you can guess the other value. It means they are or either same, or there is a direct relation where you can calculate. So let us see some examples where I have calculated the power expected density. If Rx tau is minus 2 alpha tau, then the spectrum density is the Fourier transform of this is 4 alpha upon 4 alpha square plus omega square. This can be directly computed taking the Fourier transform. So this has a high component or DC offset, and then it goes to 0 as omega goes to infinity. If I take this SXW, which is a rectangular signal, this means that the signal has power spectrum only in a particular band of window this, then the autocorrelation is given as the sinc function. If I go back to this example, x equal to a cos omega naught t plus theta, where theta is uniform random variable, we have seen this, and we have computed the autocorrelation for this, which is a square by 2 cos omega naught. Okay, and then I can break this cos omega into a summation of 2 exponential. This will ease the calculation of Fourier transform. So we know that the Fourier transform of these individual are delta functions. So the Fourier transform of overall Rxt will be summation of 2 delta impulses, one at omega naught and one at minus omega naught. And what do we get from this? This means that the power actually, the most of the signal power is concentrated around two frequencies, omega naught and minus omega naught, which basically says that there is only one frequency component of omega naught frequency. Okay, and that is also can be seen here, right? There may be phase difference, but whenever you observe this signal, you get a cause wave of omega naught frequency. Let's look at how PSD can be interpreted. Right. For this, suppose you have a random process, and we will start with a finite windowed version of this xt. So I will only redefine this random process as a xtt, which is the windowed version. So I multiply this indicator to xt. So this means that whenever t is outside this window, this signal will become 0. And inside this window, this will just be equal to xt, right? So there is xt is a infinite length signal. I am just trying to look at a particular window of it. Okay. This will help us to compute the averaging and well defining that. So now let us take the xt signal and look at its realization for one outcome. So it will become a deterministic signal. And if I take the Fourier transform of it, I'll get the, I can interpret the Fourier frequency domain and values of this signal. So XTF is the Fourier transform of XTT, and this will denote the spectral content of random realization. Okay. Now, notice that if I take the integration of xt square from minus t to t, this is same as integrating this Windows version from minus infinity to infinity. Okay. So if I windowed version of xt square. So if I take xt square and integrate from minus 1 to infinity, outside this window this becomes 0, and inside this window this will become xt square. So this and these are equal. So xt square dt from minus 2 to plus t is equal to the integration of xt square dt from minus infinity to plus infinity. And from Parseval theorem, that is equal to the integration of xtf square df from minus infinity to plus infinity. Okay, so right, so it means either you integrate the Fourier transform over the frequency, or you transfer the signal power from this, you get the power of the signal, energy of the signal. So from this, now let's take the expectation on both sides. If I take expectation, this is a linear operator, so expectation can go inside. E of xt square is nothing but Rx0, okay, which is independent of t, so I can take it out. So this will become just 2t. So this term will become 2t Rx0. And here, if you look at expectation will go inside. So this will be an integration of extf square df. Okay, now I take 2t and then put on the right hand side. So I'll get Rx0 equal to integration of 1 upon 2t e of xtf square d. Okay, and now this is true for any t. So if I take t to infinity, this xtf will become the Fourier transform of the xt. Okay, so I can also write this limitation of t tends to infinity 1 upon 2t, and then this will best become xf square. Now we have seen that Rx0 is nothing but the integration of SXFT. So if I compare these two signals, what I get is that SSF can be interpreted as limit t tends to infinity 1 upon 2t expectation of xtf square. Okay, so again, this is the frequency component. And if I take the time average, right? If I take the complete signal and look at its frequency component on the average, that will give me the power spectral density of the signal. Same way we have defined autocorrelation. If there are two signals, we define the correlation between them in form of cross correlation. So if there are two signals, random process xt and yt, then the cross correlation function between them is given as expectation of xt1 into yt2. And we denote it as rxy t1 comma t2. Similarly, the cross covariance function of xt and y2 is defined as expectation of xt1 minus mean of t1, mean of x, and yt2 minus mean of y. And then we take the expectation of it and we denote it as cxy t1 comma t2. Note that if mu x1 t1 and mu y22 are 0, in that case the correlation and covariance would be same. So based on this cross correlation function, we can talk about if two processes are jointly wide sense stationary. So two random processes xt and yt are jointly wide sense stationary if they satisfy the following two conditions. First is xt should be wide sense stationary and yt should also be wide sense stationary, and the cross correlation function should be just a function of t1 minus t2. It should not be a function of t1 and t2 separately. It should only depend on the delay. This means if I increase t1 and t2 both by tau, the cross correlation should be same. So if xt and y2 are jointly WSS, we also use this notation rxy tau, where tau actually denotes t1 minus t2. So rxt tau is defined as expectation of xt plus tau into yt. Okay, and because it only depends on the delay, it doesn't matter what is the value of t. Any value you put as t will give you the same value, as it's only a function of the difference between t plus tau and t, which is tau. Now, same way we have defined rxy, we can also define ryx. So ryx in the same way would be defined as ryx tau is r expectation of x y t plus tau into x t. So we can say that with this relation exists, that the cross correlation rx by tau is related to rx tau as that Rxy tau is equal to Ryx minus tau. And that just can be proven from the definition. So you see that the value of Ryx minus tau is given as E yt minus tau into xt. And I can also write it as E of xt into xt minus tau. Okay. And as I said, the value of t doesn't matter. It only matters the difference between two. So this is equal to Rxy tau. So let us see one example how we can compute this Rxy tau. Let xt and nt be two independent WSS process with expectation ext is mu x and ent is suppose 0. And let yt is equal to xt plus nt. We want to show that xt and yt are jointly WSS and we want to find Rxy tau. So to show that xt and yt are jointly WSS, first we have to show that xt and yt are both WSS. So xt is already given as WSS. I have to show that yt is WSS. For that, I have to compute the mean and the autocorrelation of yt. So mean of yt is equal to mean of xt plus nt, which is equal to mean of xt plus mean of nt, and that is equal to mu x. Okay, and it does not depend on time. Second relation would be that Ry t1 t2, if I compute, that will be equal to expectation of y t1 into y t2, and y t1 is x t1 plus n t1 and y t2 is x t2 plus n t2. You will multiply, we get cross terms. We get e of x t1 x t2, which will give you rx t1 minus t2 because x is a WSS process. Similarly, n t1 and n2 will give you Rn t1 minus t2 because n is also a WSX process. The cross terms where you have xt1 into nt2, because they are independent, that will be just equal to E of xt1 into E of nt2. Because E of nt2 is 0, that term will be 0. Similarly, the term expectation of nt1 and xt2 will also be 0. Now, if you look at this function, you can see that both functions are only function of t1 minus t2. So their sum will also be a function of t1 minus t2. Hence, yt is a WSS process. Now the remaining two is to show that auto cross correlation of xt and yt is also just dependent on t1 minus t2. So the cross correlation of Rx with t1 t2 is defined as expectation of xt1 into yt2, and yt2 is equal to xt2 plus nt2. So what I get is E of xt1 into xt2 plus E expectation of xt1 into nt2. This term will again become 0 because this is independent. So E and T2 is 0. And this term is nothing but Rx T1 minus T2, which is again function of only T1 minus T2. So Rxy T1 comma T2 is just Rx T1 minus T2, and it is just a function of T1 minus T2. Hence, Xt and Yt are jointly WSS. To compute the Rxy tau, we just put t1 minus t2 equal to tau in this expression, and we get Rxy tau is equal to Rx tau. Now let us see what happens when a WSS random process is passed through a linear system. So we will talk about what is a LTI, a linear invariant system, and then we will see when a wide stationary process passes through the LTI system, what happens to its spectral and autocorrelation. So let me recall that what is a linear time invariant system. First, we will look at a linear system. A linear system simply means that if you apply x1 and get output phi x1, and if you apply x2, you get output phi x2. If that is true, then if I apply ax1 plus bx2 on this system, I get the output alpha phi x1 plus beta phi x2. Okay, so the system is linear just means you can apply the scaled summation of two inputs, and then you can expect the output to be also the scaled summation of the two outputs. And invariant means that if you shift the input by time tau, the output also shifts by the same interval. Okay, so a system is time invariant if you shift a signal by tau and apply to the linear system, you can expect that you will get the normal outputs shifted by tau. And if a system has both quality linear and time invariant, then it's a LTI system. So for LTI system, we have something called impulse response, which shows the output of an impulse. And this impulse response has this also property that if you apply an impulse to it, you get this response. And also, if you have any input xx, then the output will be given as the convolution of this impulse response and the input. So if you apply xt and the impulse response is st, then the output would be xs st minus sts, which is nothing but the convolution of xt and ht. Okay, and if I take the Fourier transform of this st, I get a transfer function hf, and this has transfer function has this property that if you apply a signal xt whose Fourier transform is xf, then the output Fourier transform would be equal to multiplication of transfer function into xf. Okay. Now, if a LTI system is causal, it means st equal to 0 for t less than 0. This means if the impulse is there at t equal to 0, there cannot be any output before the impulse is applied. Then it's a causal system. So in that case, the output is just written as hs into st minus ds when the integration is from minus infinity to t. Now let us see that if there is a linear system, and if I apply a random signal, a random process to it, what kind of output we get? Okay, and we assume suppose xt is a Whitson stationary. So I would be interested in computing the expectation of yt, the autocorrelation of this yt, and the PSD of this yt. Okay. So first is the expectation of yt. Our claim is the expectation of yt is equal to h0 into expectation of xt. So expectation of yt is equal to yt can because it's the output of this linear system. So yt should be convolution of xt and ht. Okay, that is because of the property of the LTI system. So I can say that yt is equal to integration of xs into st minus ds and the expectation of that. Now expectation is linear operator, so I can take it inside. And remember, this is a deterministic function. Only thing random here is xs. So this will become integration of expectation of xs into st minus ds. Okay, now because I've assumed it's a WSS system, expectation of xs should not depend on s. That is one of the property of the WSS function. So if I take it out, what I get is EE621A, which is independent of s, and then the rest term there is the integration of st minus sts. Okay, now we have to compute this particular function. So first what we do is to solve this, we substitute s dash equal to t minus s. In that case, ds dash is equal to ds. So when I make this substitution, here I get hs dash into ds dash, and the limit stays same because it's minus infinity to infinity. So you have to subtract the compute t minus s for both, and they will remain same. So now if I integrate hs dash into dh dash, I get h0. Okay, and why so? Because if you look at here, remember that h is the Fourier transform of h. So we know from the definition that hf Fourier transform is equal to function into e to the power minus j 2 pi f t dt. If I put f equal to 0, this term will become 1, and I will get h0 is equal to integration of st dt. Okay, so this is the result we use here, and to show that this integration is same as h0. So if I write it here, I get this. So this tells me that if you pass a WSS signals to a LTI system, the mean of the output will be equal to the mean of x multiplied by the Fourier transform value at 0 or frequency 0, or you can also compute the integration of impulse response. This will give you the same value. Now let us look at the next result, that what will be the cross correlation of x and y. So Ryxt is defined as expectation of xs into ys plus t. And this is by the definition we have seen earlier. And then instead of ys plus t, I write down it as a convolution of xs and ht. So it will give you hs plus t minus u into xu du. Now I can take the expectation inside, and in that case, you can see the xu and xs are the only term which are random. So this will become integration of hx plus t minus u, expectation of hs into hu into d. Now, because the W is stationary process, this expectation would be nothing but Rx u minus s. Now I do a substitution, u minus s equal to u dash. So this will become Rs u dash. This will become t minus u dash. So this integration will become st minus u dash into Rx u dash du. And this is nothing but the convolution of ht into Rxt. Okay, so if Ryxt is equal to st into convolved with Rxt, then we can say the Fourier transform of this is equal to Fourier transform of this multiplied by this. Okay, so convolution in time domain become multiplication in the Fourier domain. So if SYXF is the PSD of this, then SYXF is equal to Fourier transform of st, which is HF, into Fourier transform of Rxt, which is XSF. Okay, so this is the second result, that the cross correlation between x and y is multiplication of the transfer function and the PSD of x. Okay, sorry, this is not cross correlation, it's the Fourier transform of the cross correlation. Then we get the next result, which is what is the autocorrelation of y. So autocorrelation of y is written as E of ys into ys plus t. Okay, and I can again apply this. I will take one s plus t same, and the other ys I represent them in terms of convolution of x and h. Then I take this expectation inside, so it will become h s minus u into expectation of xu into ys plus t into d. Now this is nothing but the cross correlation between x and y, which is Ryx s plus t minus u du. So this, then I do a substitution that s minus, u minus s is u dash. So I get this particular format, which is nothing but the convolution of h minus t and Ryxt. Okay, so if this is the convolution, then what I know that the Fourier transform of Ryt should be equal to the Fourier transform of this into Fourier transform of this. So Fourier transform of this, let's call it it's as y, which is the PSD of y. Fourier transform h minus t is given by the conjugate of the transfer function, and Fourier transform Ryx is already we said it's Syxf. And we have already computed the value of SYXX in the last slide, which is HF into XXX. So what I get is, if these are multiplied, this will be the absolute HF square. So what I get is SYF is equal to HF square into XSF. There's a typo here, it should be square. So these are the three results which we get here. Okay. So a mean would be multiplication of mean of X into H0. The autocorrelation of Y would be equal to the convolution of ST convolved with H minus T convolved with RXT. And in the Fourier domain, it means that the PSD of Y is equal to PSD of X into transfer function absolute value square. We can see one example of this. Suppose there is a white noise process, NT, which PSD is given as sigma n square. So it is constant, it does not depend on F. And if I pass this noise to a RC circuit, so this RC circuit, I apply the voltage here, noise here, and I look at the output V out. So we know that this is a linear time invariant system, and its transfer function is given as 1 upon 1 plus j 2 pi f RC. In the time domain, the impulse response will be given as this formula. So if I apply the noise here, I would get the output whose PSD will be given as sigma n square upon, which is multiplication of HF square into SNF, which is this. And you can see this is, it was a white noise, but this depends on F. Similarly, I can also compute the autocorrelation, so we get a colored noise. We will now show that the SSF is the power spectral density. So this means that the average power in any frequency band F1, F2 is given as integration of this density over this band. And of course, there are two bands both in the positive and the negative axis. So there is a 2 factor here. So if this is in fact a density, the power in any band should be given by this. This is the basic definition of density. So to show that, what we do is we pass X2 through a ideal band pass filter. So this band pass filter is this, that it allows signals between F1 and F2 band and cancels all other signals. So its output is 1 in this band and rest it is 0. So if you pass X3 through this LTI system and then you expect a output of IT, then the spectral density of Y is given as spectral density of X into HF absolute value square. So the average power of XT, average power of YT in the band F1, F2 is given as EY square T is nothing but the integration of power spectral density of DF from -infinity to infinity. So this we have showed. This is from the Fourier transform definition of SYF. Now, because it's a LTI system and SYF is given as XXF into HF square. Now HF is nothing, is 1 from F1 to F2 and 0 otherwise. So this will be given as integration of SSF df from F1 F2 and minus F2 F1. So because it's a symmetric function, you can get that this is equal to 2 of F1 from F2 SSF df. So this is what we have showed, that average power of a signal YT is given as the integration of this signal from in the band. Okay, so if you take a very small interval delta f, f to f plus delta f, you can show that this signal in that band is just SSF into 2 delta f. So this also shows that the SSF is always positive for all f, because if you take a very small interval, this should be positive. So this side should also be positive.